Hi, in this video we look at branch and bound, and I'm going to look at one particular example. Problem 1a in section 6.4, maximize 5x1 plus 2x2 subject to two constraints and integer condition on the two variables. Now without the integer condition, that's a conventional linear programming problem, which we can solve using linprog or LP assistant or some conventional method. So when you do branch and bound, that's how you go ahead and start. You use the conventional method to solve. And in this case, you get a solution of 7/6 and 3 for x1 and x2. And your optimal value is 71/6. Now, this solution is not allowable because x1 is not an integer, but this does give us some information. What this tells us is that the integral solution cannot have a larger objective function value than this, right? Because this is adding an additional condition. Adding an additional condition cannot give you a larger value for your final objective function, right? Furthermore, we know that the objective function for an integer solution has to be an integer, okay? So the best solution with this integer condition cannot achieve a result better than the biggest integer that's smaller than 71/6. The greatest integer less than 71/6 is 11. Okay, so this is the best possible solution, z equals 11. Now, notice that if I could just find a solution with z equals 11, I'd be finished. If by trial and error or by some method, that would be fine, because I know I cannot do better than this value, right? But at this point, we don't see any solution that comes to mind. So instead, we need to solve two sub-problems. Now, we know that the solution cannot have x1 equal 7/6, so we split into two branches. Either x1 is less than or equal to 1, or x1 is greater than or equal to 2. These are the two closest values of x1 to this value here. Now, if I had two non-integer values, I'd have to just choose one of those and then continue. Right, but I do have two subproblems, which I can solve using my conventional linear programming method. I simply add that constraint and I get two additional problems. Okay. Now, if I do this problem here, then I get a solution of 1/27 with an optimal value of -75/7. Okay, optimal value is 75/7. It comes out minus because you change the sign to solve a minimization problem, okay, to solve a maximization problem. Okay, so the bound here now is the greatest integer less than 75/7, which is 10. So if I follow this branch, I can't hope to do better than 10, right? I can't hope to do better than 10 for my objective function. All right. Now, if I follow this branch, then I have x1 greater than or equal to 2, or I change that to minus x1 less than or equal to -2. I solve that using my conventional methods. In this case, I have my 11 as my optimal value, but I still have a non-integer solution. Okay. So at this point, I can't rule out either branch. I really should continue with both branches. Now, I think the best strategy at this point is that this branch has better prospects, because it gives a bound of 11 instead of a bound of 10, right? So I would go ahead and do this branch first. Now, when you do this branch, you have to look at the two cases here. We know that 1/2 is not possible for x2, so we have to break this into two cases, x2 less than or equal to 0, and x2 greater than or equal to 1. Okay. Now, x2 less than or equal to 0 is just x2 equals 0, because, of course, x2 is positive. So that gives me 2, 0. Now, if you plug in 2, 0, it turns out that you actually get 10 for your value of the objective function. All right? So you're actually done. The reason that you're done is that if I follow this branch, I could not do better than 10. Right? And I should check, I really should check that 2, 1 does not do better. And I think 2, 1 actually doesn't solve the equation. So I should check 2, 0 or 2, 1. But 2, 1, 2, 0 meets this bound. So I don't have to go look further down this branch because my solution here meets the best possible result I could get from this branch. Okay, so you can verify if you plug in 2, 0 here. Let's just do that. If I plug in 2, 0, here I get 10, and here I get 12, it's less than 13. Here I certainly get minus 12 is less than 14, and then I have integer. If I try 2, 1, that would give me 10, that would give me 4. Well, if I do 2, 1, you can see that that's not going to work because 2, 1 would give me 12, and I already know that 12 is not possible. Okay, so that's giving me 2, 0. 2, 0 is going to be my best solution, and I don't have to go any farther. Okay, so the summary of this method is that you do solve equations, you do solve linear programming, conventional linear programming, then you look at your subproblems, and you examine your subproblems for the best possible solution. Okay. All right, and if you and there are some cases where you can rule out one branch or another, and you should follow the branch where your prospects are the best, where you have the best optimal value. But at this point, I cannot rule out either branch until I find a solution over here that meets this best possible bound. So you may have to branch off of branch. You may not just have 2 branches. You may get to 4 branches. That's possible. Okay, but the point is that once you get an integer solution for your branch, then you stop. Or once you get to a place where once you get non-feasible, then you also stop. Okay, so you can see examples of that in the book. All right, so I hope that gives you some idea of how you branch and how you know when to stop branching. Okay, but you do have to keep branching off of solutions until you can rule them out. Okay, thanks for watching.